discovered first planet that may orbit in triple star system. The Lambda Orionis region is one of the most studied and best-known star-forming regions in existence. It is located near the star of the same name in the head of the hunter represented by the constellation of Orion. And right there, among the hundreds of forming stars, there is also GW Orionis, a system in which just in these last months we may have found the first planet able to orbit even around 3 stars. We are used to think that all planetary systems are like ours, with only one central star, regular and a bit flat. In reality, most stars are born in clusters of 2 or more stars, which makes the formation of planetary systems much more chaotic. So what happens in these cases? Well, everything obviously gets complicated. Let's go and see why. Surely you too, as a child or teenager, loved Star Wars and its alien settings madly. Like, for example, the one where Luke meditates on the future in front of the sunset of the 2 suns that warm Tatooine, his home planet. It is such a unique scene because of that incredible sunset, which reminds us of how alien the world Luke inhabits is to ours. But very recent news tells us that probably in our cosmic neighborhood, there is a star system that is even more spectacular than Tatooine's. Are you wondering where? Okay, we'll get there, but first we need to try to understand what we are talking about, and especially to answer this question: how many stars can a planet successfully orbit? For a long time, we had only our own solar system to look to, as we were the only star we knew of with planets surrounded it all. It wasn't until the 1990s that we found planets orbiting other star systems. Even though stars come in singlets, binaries, trinaries, and even greater numbers of multi-star systems, we'd only ever found stars orbiting 1 or, at most, 2 stars. Even in systems with 3 or more stars, planets have only been found orbiting 1 or 2 of the stars at once, with the other stars farther out. There had been 2 main schools of thought as to why this was the case. One idea was that planets can orbit stars either closely, in which case their orbits are dominated by one central star, or a tight binary star that supplies their gravity, or far away, as long as they're far enough so that however many stars there are behave like a single mass. According to this idea, the only reason we have not seen planets in wide orbits around trinary or major systems is because they are difficult to observe. But a rival idea is that wide planetary orbits around 3 or more stars would be fundamentally unstable, and gravitation would quickly drive out any such planets. When stars are born, they typically form in large, massive star clusters, triggered by the gravitational collapse of a molecular gas cloud. Instead of forming in isolation, typically hundreds, thousands, or even as many as millions of stars can form all at once. A wide variety of star systems form inside, where only about 1 in 2 stars form in singlet systems like our own. About 1 in 3 stars are found in binary systems, where 2 full-fledged stars dominate their solar system. 1 in 10 compose trinary systems with 3 stars, 1 in 40 are in quaternary systems, and about 1 in 100 stars exist in systems with 5 or more stars, all bound together gravitationally. These star clusters consist of star systems with widely varying masses, and over time they gravitationally interact, causing lower mass star systems to get ejected while higher mass star systems sink to the center. Over longer timescales, typically around a few 100 million years, these star clusters dissociate, populating the galaxy with the individual star systems that formed within them. But while the stars are forming, something else forms along with them: planetary systems. Beginning with observations from the Hubble Space Telescope, humanity began seeing for the first time these long-predicted planet-forming systems around young stars and protostars, protoplanetary disks. Rotating around young stars, these dusty disks develop instabilities, where some regions of the disks become slightly denser than others. Regions of greater density will preferentially attract more and more of the surrounding matter to them, eventually growing into protoplanets or even full-fledged planets, sweeping up the dust and creating gaps in the disk, leading to a series of dust rings instead. In theory, what should have happened in all of these systems was the following. Protoplanetary disks develop regions of instability. The largest of these regions grows and attracts other masses. This eventually leads to the formation of a planet, which will sweep dust and gas out of its orbit, This creates gaps in the disk. Although it has taken many years and numerous technological advances to directly observe these features, we have now found a large number of protoplanetary disks with these characteristic gaps, which are evidence of forming solar system. However, a planet cannot form everywhere. There is a problem in physics when you have multiple masses orbiting each other. The fact that if you have more than two masses bound together, the mutual gravitational pulls exerted will lead to unstable orbits. Over time, planets can be ejected, thrown into a star, or even pushed into orbits where they will collide with each other. Simulations of our solar system indicate that this happened in the past. We believe we had a fifth giant planet that was ejected long ago. We also know that a Mars-sized body collided with the Earth in the early days of the solar system, creating our moon. And even in the distant future, simulations indicate that there is about a 1% chance that one of the four inner planets will be ejected before our sun runs out of fuel. When you have multiple stars in the system, however, you should be prohibited from having planets orbiting any of the stellar members at about the distance that separates the stars from each other. In theory, there are three places where planets can form: near a single star, where the gravitational force is dominated by that particular star; around tight binary systems, where the two stars actually behave as one mass; some combination of the first two scenarios, where a planet is far away from some of the stars, but one or more stars is even more distant. However, when it came to trinary systems, these three scenarios didn't appear to all play out. For some reason, in fact, of the 32 trinary systems that were observed to possess exoplanets as of early 2021, all of them only had planets that were either close in around one star or were close in around a binary, with a third trinary member much farther away. There were no known systems where a planet was found orbiting far out, beyond all three stars in a trinary system. At least until today, that is. Until the radio telescope ALMA has revealed something more about GW Orionis, a very young triple star system, less than 10 million years, in which the narrow binary, formed by the two nearest stars, just 1 astronomical unit away or 150 million kilometers, is orbited by a third companion, about 8 astronomical units away. Distant from Earth 1,330 light-years, GW Orionis has long been known as a star system affected by the presence of a shapeless disk of dust, but only recently has been finally investigated by Atacama Large Millimeter Submillimeter Array, ALMA, the most advanced network of radio telescopes ever built on Earth, and humanity's best tool for imaging these protoplanetary disks directly. Since it became fully operational in 2013, ALMA has revealed more details about more systems. When it managed GW Orionis, it found something truly spectacular, the most massive of any planet-forming rings we've ever seen. The observations revealed that around the three stars of GW Orionis, there is a disk of dust that surrounds them all. A disk so-called circumtriple formed by three rings, the first with a radius of 46, the second of 188, and the third of 366 astronomical units. To get an idea of these dimensions, the orbit of Neptune with 30 astronomical units of radius is 10 times smaller than the last ring of the GW Orionis system. The oddities do not end there. The disks, in fact, do not lie on the same plane, but are strongly eccentric and inclined with respect to each other, so that the system resembles a giant compass suspension gimbal. Pay attention to it. Things get weird when you look at the thing more closely. For one thing, the third star in the system, called GW Orionis C, doesn't orbit in the same plane as the two stars in the binary A and B. But it's the disk around them that's truly bizarre. The disk, which around most forming stars is usually quite flat, has been warped and even broken. High-resolution observations show parts of it have been sculpted into a series of rings. The middle and outermost rings are tipped to our line of sight, so they look like eclipses, in the same way the rim of a glass seems elliptical when seen from an angle. Both the outer rings are coplanar, sharing the same flat plane, but it's tipped with respect to the binary orbit. Strange indeed, but the most interesting thing of all is that ALMA was able to see in the disk the presence of some gaps, regions free of gas and dust, the largest of which is located at a distance of about 100 astronomical units from the central stars, between the inner and middle rings. To visualize this, imagine something similar to the Cassini division that bisects Saturn's rings, obviously on a hugely superior scale. The simulations immediately set up by the researchers have shown that the effects of tidal interaction between stars and disks are not sufficient to explain the gaps, and therefore the only possible explanation is that of the presence of one or more planets in formation, although at the moment not yet identifiable. Planets that, in traveling their orbits around the three stars, are sweeping away the dust and gas they find along their path. The first exoplanets and the first circumstellar dust rings found to orbit around at least three stars. The possibility of a planet, or more than one, forming from these dust disks is justified by the fact that astronomers believe the three rings each contain enough mass, 75, 170, and 245 times the mass of the Earth, respectively, to support the formation of at least one giant planet each. For the first time, we can not only go beyond Tatooine, with three stars in a planet's sky, but beyond all other trinary systems, to a set of planets that orbits around all three stars at once. And their possible existence suggests that planets spring up in all sorts of places, even here in the most bizarre of systems. Even a world orbiting 4 or 5 or 6 stars at once. Who knows? The view from here, going back to the scene where Luke contemplates the sunset from his home planet, would be quite similar to that of Tatooine. Two suns would be seen. The narrower binary would indeed appear as a single point of light in the sky, separated by the third star, but the light would be more sparse, containing the 100 AU distance of the hypothetical planet, and the three stars would be entirely point-like. But let's take it easy. These conclusions are still approximate and are based on mathematical calculations, so there is still need of verification. In the coming months, new observations of the GW Orionis system are planned with the ALMA radio telescope. They will certainly offer new information, and Jeremy Smallwood's team hopes that they will also include evidence for the existence of at least one exoplanet. We struggle to figure out how our relatively simple single-star and 8-planet solar system works. Such are the interactions in it, both subtle and gross. But there could be much, much weirder things out there. We've already seen some, and many more await both our discovery and our understanding.